Okay, so my name is Rantaeskola. I work for Simplygon as a product expert. With me here today I have Zach Litton from Telltale. I would just start by going into a little bit of a part of a presentation I've given a few times before I hand over to Zach. So this is me, some of the games I worked on, and some of the companies I worked for in the past. Right now with Simplygon, and if you want to find me on Twitter, that's me. I don't tweet much, so anyhow, Simplygon. We consider ourselves being the gold standard for 3D optimization in high-end video games. We work with clients all around the world. And this presentation, a little bit about our experiences talking to these developers. Now, there's usually a misconception about Simplygon that it is a lot generation tool, and you work through, for example, Max, Maya, or Unreal, Unity with it. But a lot of the really big values in Simplygon comes from the custom integrations that a lot of our clients have done. Here are some of the examples. And this presentation is going to focus on custom integrations towards the Simplygon SDK. So what's up with the title? Why keep the game running? Well, let's go back a bit into the past. If we go back to the 90s, many games were built by 2-3 guys, or girls, but mostly guys back then. When the build broke in a game, it was not a matter of, it wasn't a big problem. You just turned around, slapped the guy next to you in the head and said, fix the build, and it was fixed. Now, teams grew quite fast, and well, in the early 2000s, it was easily 40 people in big games working together, and a broken build became a big problem. So what we did is we started being more careful in how we coded. We added coding practices. We made sure that the game was running all the time. We still had the problem of the lonely build engineer sitting there somewhere where you had to go and ask him, well, can I have a build? And he'll start compiling, and then after a while, you'll have to go to some obscure FTP and grab it and upload it through some weird program to your PS3 or PS or Xbox back then. So we solved that problem by adding huge farms where you built the game continuously as soon as it could when changes happened. The asset pipeline has not received the same amount of attention over the last 20-30 years, which is a bit sad because it's not just about keeping the game running, it's about keeping it running in a close to final state. And the thing is that assets affect performance immensely, as most of you know. And if not all assets are in the optimized format, the game will run slow and you can't make calls on whether you're good in performance or in memory early on. So why do we optimize at all? Now many here probably knows this, but I'm just going to go through rapidly a few of the reasons why content needs to be optimized to utilize platforms today. In the past, the reason why you were reducing polygons on assets was because the polygon pipeline was not very fast on GPUs. So you couldn't push that many polygons per frame. Nowadays, sure, it still has a meaning, but the biggest reason is because of how the shading pipeline is constructed. It's not very efficient to have small polygons on screen. That means that shading has to be done a lot more time per pixel. So big polygons is preferable. So reducing polygons on meshes means that you have bigger polygons, means that they're cheaper to shade. We have huge amounts of memory at our disposal today. 8 gigabytes. I mean, last generation of consoles was 512. 8 is insane in comparison to that. But there's still a bottleneck wave that will not change over this generation. It will actually take a long time on PC as well to change. And it's how much data you can transfer every second. And right now on PS4 and Xbox, that limit is somewhere around 100 to 200 gigabytes per second. It depends on how you structure things, but let's say 100 gigabytes is a limit. If you're going to render at 30 FPS, which is the least for a game, what you have accessible is 3 gigabytes of data. If you're doing 60, which many games strive for today, you're at 1.5 gigabytes per data per frame. If you're going for a VR experience, we might be talking 120 frames per second. Well, then you're down to 750. So we're down to the same size limits as we were in the previous generation. This is probably the #1 reason why content needs to be optimized: draw calls. Today's most common bottleneck is the number of draw calls per frame. So reducing the amount of draw calls is one of the main reasons why content is optimized. Animation cost. Now in character-driven games, or any games with a lot of rigged assets, animation calculation tend to be a huge bottleneck on the CPU. It's not uncommon to have 10-15% of the CPU consumed by this. So reducing the amount of animation calculations can free up a lot of valuable CPU time. Vertex transformations. This is one thing that most people don't think about, but now we're pushing so many polygons every frame that the time it takes to transform a vertex to world space actually starts to stack up and consume a lot of time. Some engines does it on CPU, some does it on GPU, but anyway, it will be a significant cost all in all. So reducing the amount of vertices that needs to be transformed is, of course, a big gain. And finally, reducing overdraw. It's no good idea the more times you have to shade a pixel, the more it costs, of course. So, before this presentation, I've done a little bit of research, and I've spoken to a few people I know and some people that I work with about how much time is being spent on optimizing content. So this is shared by a AAA game, and let's say a medium-sized AAA game. They calculated that they spent 2 hours optimizing environment art, and in their game they had roughly 1,500 models, and 24 hours on the 50 characters. If you sum all that up, that project consumed roughly 26 man-months of optimization work. Another game, which is a quite large AAA game, there was a TA there that I know quite well, and he told me they have roughly 5,000 assets. He said that the number of assets has not grown over generations, it's just they have become more complex. One metric that he had found was that you tend to forget that an asset is not fixed only once. Each asset in a game, in his experience, is touched 3.6 times. Which means that if you, as I just made an assumption here, if you spend 1 hour of optimization every time you touch the asset over 5,000 assets, what you'll be looking at is roughly 110 man-months spent on optimization in this game. He also shared with me that roughly 30% of an artist's time today is spent on optimizing content. The final stats I have is, this is from our backend. We can see when people, when somebody starts using Simplygon, we get just an activation request. We don't know what's happening, but basically we see how many times it's being activated over the course of 90 days. We have 5 AAA games here. These all average out to roughly 100 optimizations per day. These are companies that are using Simplygon in an automatic fashion. If we sum this up together, and we do an assumption that it saves 10 minutes, which might be low, and a project length of 400 days, 2 years, which once again is probably low, it's about 40 man-months of optimization work in a 2-year project. So to sum that up, in a AAA project, automating part of the asset pipeline can save up to 25 to 100 man-months of optimization work. Now, before I hand over to Zach, I'm just going to say one final thing. When you're automating optimization work, one thing you tend to forget is the biggest save you're actually doing is taking away the manual reviewing. Because when you are manually creating LODs or even generating LODs on an artist seat, what you're doing is looking at them afterwards and probably fixing and tweaking and tuning a little bit. But if you repeat that for 5,000, 10,000 assets, that's going to be a lot of time. If you automate it, what's going to happen is that they're never going to be visible until they're in the game. And thus, the only place you can review them is in the game. And if it doesn't look broken there, nobody's going to spend time fixing them. So that is the biggest gain of considering automating the optimization pipeline. Zach. Zach is going to share his story of how they approached it at Telltale.
Cool. Hello. My name is Zach Litton, and I am the VP of Engineering at Telltale Games. And I've been at Telltale for about 5 years. So I've kind of seen our pipeline through almost a dozen seasons of products. I'm going to talk about how we integrated Simplygon into our existing automated asset pipeline over the course of a few weeks before our Game of Thrones game. First, I'd like to tell you guys a little bit about Telltale development, in case you're not familiar. Telltale is an episodic game company, and every year we strive to do 3 seasons, 5 episodes for each of those seasons, and we typically run on 8 platforms, which is often 13 unique builds that we have for every SKU. If you do some math, it means that we are doing at least 180 builds that are shipped to the consoles, 120 different configurations for our assets, and over 9,000 builds a year. And this does not include patches or other builds. These are builds that we intend to make for running on the platform. The other thing about Telltale development that's a little different is that we have people who build our game in our tool set. So they'll build the Game of Thrones game or another one. And then using automation, we make sure that that will run on mobile devices, desktops, every console. We do not build custom assets for every single console. We try to build them once and then have that game run everywhere. And this is how we are able to run on so many builds a year and so many platforms, is because of our heavy reliance on this automation. But developing in this way has a lot of challenges and is not something you can come into lightly. Every single platform has unique resolution that you're going to hit to. And really that means unique pixel density for when you're talking about a 3-inch iPhone and the 480 pixels tall, how much you can see in that phone. Every platform has different audio, GPU, CPU capabilities. They all have unique game download footprints. So sometimes you can have a lot of assets, or sometimes they must be very small. And it's very challenging because of the numbers I said about scale. With these nearly 20,000 assets builds, we're doing 180 million unique assets that we build over the course of a year. So it's just a great number of data that is being churned through. So how does Telltale approach this problem? So Telltale approaches this by basically defining specific tuning parameters for every asset type. So textures will have the final size you want them to get at. Audio files have compression levels. Animation can have error percentage metrics. And for every asset type, we do this and get as much data as we can to drive creation of that asset. Once we have those parameters built per asset, we then have another system that goes through and organizes which of our assets are going to fall into what category of those parameters. So if we have high resolution PS3 assets or PS4 assets now, the parameters that are used for those are very unique to the PS4. So we could put all the assets into that bucket or container for the PS4. We have a large organization system around that, so that even on a certain platform, some assets can be very high and some assets can be very low, depending on how they're used in the game. So a character's face would be a very important asset, whereas maybe a background jug of water would not be as high of priority. The third part of our approach is where we integrate kind of human interaction back into our tools. These are in-engine tools we have where we're able to tag or tune certain objects on the fly to visualize how they would look with different parameters, so that we can look at the game running on a phone and decide that the background texture is blurry and we want to try to increase its quality and look at it there and very quickly get that back and look at it. And this can be done entirely at the end of the pipeline as opposed to the beginning, so that we are able to tune the experience for the particular device. And then, of course, because of the number of assets, we need to heavily use caching so that once we have good parameters, those assets are only really built once. This is kind of how this looks visually. We have people that their job is to set up good initial parameters for every type of object. So good initial mesh parameters, good default parameters, so that even when a game is just starting up, we can use our defaults from a previous game and the assets will be automatically reduced to what is typically been appropriate on a certain platform. And then as development goes, we can go back in and make those more accurate as the development goes on to get our final parameters. At the exact same time, we have the rest of our development team that is making data for the Game of Thrones while we're tuning it. So even if one scene is done, that allows us to go in and start working on tuning it while the other scenes in the game are still being built. How this looks in practice is the server farm every night is taking the data from the build tuning, taking the data from the game, figuring out what has changed. Is an asset already been developed in the cache? Did we change parameters? Has the asset been iterated on? And is building new builds every night for every platform. So the next morning we will come in and have all of our builds for every one of our game with all of the updated parameters capable of immediately going into quality assurance. So how does Simplygon fit into this? Well, several years ago when working on the Walking Dead game, our environments were fairly sparse. They have, maybe 5, 6 characters on screen, and the style of art did not lend itself to a lot of geometry. When we worked on the Game of Thrones game, as well as our Borderlands game, this changed a lot. The nature of the environment meant we had really complex scenes to build in complex environments, like this one, where we're recreating the intro for Game of Thrones in our own engine with animation and meshes. We also had much larger scenes, larger fight scenes, more complex backgrounds, and probably twice as many characters that we wanted to get into the game. So we couldn't fit everything in the same way that we would in the past, where our existing tuning parameters weren't enough. So, as mentioned by Samuel, when you're looking at optimization, you're always looking at bottlenecks. So for us, typically, texture reductions, making sure we get the appropriate size texture for pieces of the face, for the legs, for the environment, had always made a huge impact on us, and we had always developed tools around that, and it was very useful in kind of getting that extra performance. But these bigger environments presented challenges as we just still had too much to draw on the screen. And on several of our platforms, it was just simply too much drawn geometry. Again, for all the same reasons that were detailed, where it was animation as well as draw calls. So this had to be reduced, and we weren't really sure what to do. The product was probably 3 or 4 weeks from shipping, and we were just having too much performance because of this content. So what were we going to do? I think the typical response when we had occasionally run into this, and I think a lot of developers do, is you need to go hand reduce assets for certain platforms. So make a lower res version of the model for a platform that can't support that capability, or hide assets on a certain platform, but just basically start to bring the artists into looking at the specific platform, which very much was against how we developed, where we always rely on automation to try to fix these issues. It's very problematic to go this approach. You're going to have a very hard time doing this, like for us, where we want to have the same content on every platform, because it is a handcrafted movie-like experience where an artist putting a piece in that movie, it's important for the experience. It was also extremely time intensive, with only a few weeks to go before we needed to lock down the content for us to go back and change anything for a certain platform. And I think the third thing that makes it very difficult, that was also touched upon, was that it's very hard to judge success when you go back to the original art asset and review the art and then see it in game and see if that makes your game more optimized. That is a highly inefficient pipeline that will take a lot of everyone's time and build engineering to do. If you can have an automated way of doing it, you can easily adjust your parameters, check your success, and move on. So the way that we decided to approach this was we had decided to integrate Simplygon into our pipeline and add the ability to tune mesh parameters for the game. So we had reached out to Simplygon, who we had met at another conference, and decided to try to engage them in the few weeks that we had. So this is how our time went. The first week, we integrated their SDK. This was actually very, very quick and probably took 2 days. We just took our own internal mesh format, converted it to Simplygon's mesh format, added the parameters that Simplygon already had to specify the reductions we wanted, and then converted it back to our own mesh format. In between, they have a convenient object viewer, which we used to just get those parameters even quicker than a build to see how they would look. And honestly, in the first week, we just guessed at the right numbers for the assets. Just anything that we tried, we needed to get it in there to see what sort of success it would bring us. This is some of the initial art from QA after our week 1 integration. You can see that there are some seams as the meshes in the environment have pulled away a little bit, which was a common initial problem that we had. Another shot here, you can see that there is missing geometry on very thin objects, and some of the shapes are entirely optimized away. Additionally, the characters' faces, which were so important, had a lot of rough edges on them. Particularly in this shot around the ear, you can see it's not the nice curve that you would want on a face. And these were all with our initial parameters in the first week of integration. So, all in all, we definitely had issues where there were seams when big geometry was connected, butted up together, and then kind of optimized and did not perfectly pull apart. The faces didn't really compress as well as the bodies because it did not look as good with all the subtlety in a human face. We had issues with animation interaction to where very careful animations did not perfectly match up. And we had some disappearing thin geometry. However, we also had nearly a 10 to 20% improvement in our frame time, which is a huge amount to get for a week of work. So what did we do while still in that first week to try to address these? The very first thing we did was contact Simplygon. They helped us to understand ways that we could not have the seams pull apart, that we could tag certain parts of the mesh to not compress as much, and they really helped fix a lot of the very simple issues we were having, as well as just understanding what the error metrics were going to do. And it was very quick to get that. Additionally, we used a lot of our existing conventions for asset names in order to make subtle adjustments. So if we had, for instance, characters as a very easy one, let's not compress those as much. Certain things like swords and jugs and things in the environment, let's do those a little more. But we just took advantage of our existing systems in order to do that. The last thing we did, and we spent probably another day or two on this in the week, was we really just iterated a lot. Because it was part of the automation pipeline, we could adjust a value, make a build, drop assets on, and play it. And we could do that 100 times in a day with somebody from QA or an artist just sitting there and watching. This really allowed us, because we didn't have to go to an original piece of art and push it all the way through, but could just do it at the end, to find the right values quickly. So, after the first week, where were we at? We had fixed all of the major issues by the start of that second week, but we still had some very subtle ones that were a little harder to notice, but were still important. In particular, this one is the thin disappearing object, which happened when you had a very, very large environment mesh with very small pieces inside of it. In this particular case, the arrows. So we were close, but we were not ready to ship with what we had. We still anticipated needing hours of hand-tweaking content to work out the edge cases. We talked about ways that we could have the artists paint important pieces so that we know that those would not get compressed as much. Or we could break apart the geometry into more different pieces. But all of that pushed us back up the pipeline, which we never want to go back that direction because everyone is already busy building the game. They don't want to be dealing with every individual platform. However, at the very end of the day, we still had improved performance, not as much as initially we had, but still another 5 to 10%. And most importantly, the bottleneck had shifted somewhere else. No longer was the amount of drawn geometry the biggest concern. There was other concerns to reduce, so it was getting into an area where we could optimize elsewhere. So to finish and really get it to a level where we could ship, we went and tried to integrate our tuning. So the way that we did this is we have tuning tools that allow us to tag object lists in the actual running builds or in our tool sets and make sure that we list them or as this is not looking good enough. And in particular, our tools worked on per texture basis, so we could tag textures to need to be higher or lower quality based on how they were looking. So because this tool had been very effective in the past, and we had quality assurance people at the end of the pipeline who were already using this in order to get the content ready for platform, we basically adapted it in order to paint vertex weights for the meshes. So in this way, we could take a character's face or an arrow texture and indicate in the build that it was disappearing, that particular texture, any part of the mesh that it was touching needed less reduction or needed no reduction at all. We could basically paint mesh quality using these tools. And that data just fed in, like in this slide, to our list of textures that were quality and changed the way we organized it. So this hookup probably took another couple of days for us to do. But what it gave us was now a way to set basically our mesh detail level based on every platform and the target resolution. So now the platforms that had smaller resolutions could easily be tagged to have much lower size of mesh, and then had a second pass gone onto any that were not readable on that platform to look better. So if anything on a phone was much, much smaller but was still impacting the experience, like a close-up on a face, we could really easily improve that quality. So this, generally means that all of those bugs didn't need to be written up by QA, handed to art, fixed. Instead, we could just take single passes through an entire episode and quickly fix all of the visual elements that were impacting the performance and get those ones fixed up. So, future work that I think we want to do. I think one of the big ones that we can do at Telltale is we can use more analysis to help in our tuning based on knowledge of camera and the target platforms. Our games are highly predictable in what you see. You can always we know as we develop all of the camera angles, where the characters are going to be, all of the placement of objects, we know as we develop because they aren't wandering around an open world. So I think one of the things we're investigating is, can you take that predictability of where your content's going to be, and can you automatically make tuning adjustments based on that? This way, we could basically overnight, we would have farms of computers running through all of our game automatically and deciding that objects far from the camera would automatically have lower initial meshes and texture sizes, which would give us the ability to not just rely on LODs, but also just ship the best custom fit content for that platform, reducing the download size and everything else. I think also the better we can prove that this pipeline works and that we can create, optimized looking content on individual platforms so that it looks, just as good on, or looks as good as it can on a mobile phone, as good as it can on a PS4, the artists should have greater latitude to build their content up front. They should be able to build, an artist can building, if you ask them, they'll definitely say they would rather build a much higher, nicer looking version of an object than to try to build within a certain specific limit that might not be natural for them building that. So giving them that latitude, they're going to create what's comfortable for them. We use the automation to generate the level that we feel is appropriate on the platform. And then lastly, you have people playing the game in your studio deciding what is actually impacting readability and changing it. So it really is the best of all worlds where the artists create art, the technology splits it for the platform, and then lastly, your quality assurance makes sure it's as good as it can be. And I think the last thing we definitely want to do is continue to use more of the Simplygon technology pipeline. We integrated this very quickly over a couple of weeks. However, I think there's a lot more technology we could absolutely integrate and have since integrated into our current pipeline. I think also one thing we want to go that wasn't on this particular one was you can learn a lot by running all of this automation all the time on your platforms. We use a lot of the analysis to know how much we're reducing our textures. So if certain, our textures or meshes, to know, are we being wasteful in certain areas? You can get very good analytics about your pipeline by doing this. I think that's all of the stuff that I had on there. But it worked very well in the end, and the content shipped.
So, thanks, Zach. I want to wrap this up by just going through a number of use cases that would be common in games where I feel like this should be possible to automate in different ways. So the first one, this is the given one, an automatic LOD chain, of course. Basically, the artist creates the high-res assets and all the LODs are generated behind the scenes, checked into the repository, and reviewed in the game. Many games today are built using modular assets, especially Unreal, and I think a lot of custom engines use this technique as well. The problem is that tends to generate a lot of draw calls, these kind of assets. On the back end, or when, for example, baking the level, if these assets are merged together to become one object, you can typically save a lot of texture space, a lot of polygons, and also reduce the draw calls. As Zach mentioned, artists should build content as it's as it's comfortable for them. So for example, we have this crazy car here, 2.5 million polygons. Now this is going to be used in a scene created by me, where you're just going to have a number of these in a parking lot, for example. Now, let's just plug them in 2.5 million polygons, and then when the level is being baked, we just reduce them to optimal size. This is reverse what it should be. On the right-hand side, we have a city scene. It's 400,000 polygons and some, and 89 materials. In games where, for example, the player can go into this city and explore it, but then also fly over it, we need some way of creating cheap representation meshes. So this can be automated, possibly not totally. It might be that the artist has to tell that these assets can be grouped and generated as one representation mesh, which is the left-hand side. 9,800 polygons, one material. Animation cost. Many games have a problem with that, or at least it soaks up a lot of CPU time. Simplygon can be used to reduce animations, especially if you're making games like Telltale for different platforms. It can be helpful to reduce some of the least influential bones in the process. So here is Unity Shan, where we're taking away 50% of the bones. A feature that is coming up now is Occlusion Meshes. So here we have a rabbit, and the black meshes there, they're occlusion meshes. For games that use occlusion culling, which is becoming more and more interesting, generating or building these occlusion meshes will be very time consuming. Simplygon can generate good occlusion meshes in the background without any artist having to spend time on that. So to wrap things up here, this is the pipeline, or kind of the schematic of a pipeline. If we look at it, we have the high-res asset up in the right-hand corner there. The artist is only concerned about that. When the artist is done with this, he checks it into the source control. Then behind the scenes, there is an automatic optimizer that knows that, I need to do something with this asset. We have a number of optimization controls, or better word is actually tuning controls, that tells Simplygon what to do with this asset. It spits out an optimized asset and checks it into an asset repository, which is basically a cache that keeps all the optimized content and keeps it in sync with the source content. Finally, we have the build server there that when it's spitting out the game for the different versions, it knows which assets to use for which platform. And without the final little thing there, the fix list, we'd still be stuck in doing a lot of manual reviewing of optimized content. The fix list here is basically the representation of a feature that allows QA or artists to check what assets looks like in the game and flag them for either manual fixing or just more care in the optimization. Perhaps don't optimize as hard. So that's pretty much what we had to share today. So any questions? Would love to answer that.
今係の者がマイクをお持ちします。少々お待ちくださいませ。
Yeah. Yes.
Thank you, valuable information. I'm a Square Enix programmer, Kosuke Namiki. So I'd like to know more detail about object tags.
The object tags?
Yeah.
So,
buckets.
Zach-san, what means object tags? Do you mean level designer can add something tag to model or object from level editor?
So the places where we tag is usually done not by a designer. Usually that's part of the tuning staff that is preparing the objects for the platform. So once we have the once we have the game running in high quality art design format, then people come in and look at how automation brought that onto platform. So they'll come in and see the level on a phone or on a particular console. At that level, they can start tagging things like the face or like the little arrow example. They can tag the arrows, that those are being compressed too much. And then go back to the tuning parameters and put those arrow objects into a bucket or an organization that will make them less optimized. Samuel had mentioned, sometimes you either have to fix the asset by hand or change the automation. We always just change the automation. There's almost never a manual fix that we want to make to it because of the speed of development we work at. But yeah, it's usually done by people closer to the end who have seen the really the version, and then are playing it on another device and getting the best fit for it.
Thank you very much.
他にご質問のある方は挙手をお願いいたします。
Okay. Well, then it was very good explanations by us. Well, feel free to reach out to us. We'll be around a little bit here. Okay. Thanks for your time, guys and girls.
以上でセッションを終了とさせていただきます。